Algeria University. I'm graduate of University in Algeria, and I'm presenting my work on software pipelines for timing with Pharo. So, let me first introduce myself. I'm doing a PhD on the topic of software runtime adaptation. And the approach I adopted is based on software product lines or software factories. So what I do usually is prototyping new algorithms for software product lines based adaptation planning, which I will not explain today, but actually what I will present today is how I exploit one of the ideas I developed for software adaptability using software product lines to do reasoning on feature models using this dependencies between features. So the idea is to provide a simple API to do complex reasoning on feature models. Okay. So first of all, what are software product lines? Software product lines are just another step towards the industrialization of software development. This is to enhance or to reduce costs and time to market. Software product line usually addresses a particular market or segment, market segment or domain. For example, Renault use it for automotive, and Nokia uses it for smartphones, but it's used also in many other domains like video games, things like that, and web, and etc. So software product lines usually can have impressive impact on costs and delays as soon as the segment domain, the market segment of the domain produces a lot of products that may vary from each other, but that have many common components. So software factory. Software factory is a set of methods and tools that use a set of core sets, which is something very usual in software development. But then you have this notion of variability information or explicit variability expression. So for example, one variability information could be that all the phones must have a set of common components, like, for example, all phones must have a battery, screen, a microphone, and things like that. Another variability information is the variability, how products may vary from each other. For example, a camera could be a high-definition camera or a simple definition camera. And sometimes we have also this kind of rules, meaning dependencies between components or between features. For example, an HD camera requires an HD screen. This is just an example. Okay, so this is a key idea in software product lines: the explicit expression, expression of variability information. There's another thing also called selection policies. So selection policy could be, for example, that if we want to target battery life, we should exclude large screen or HD screens. Or if we want our cell phone to be used for video games, it should require more than up to i5 processors and things like that. Okay. And over getting different requirements from different clients, the software factory produces more or less automatically different products. So we have clients with specific requirements, we produce a specific product, different clients, different products. So, how is variability information expressed? So we use usually feature modeling. So feature model is a set of the features of the software factory. We have parent features. So this is, for example, a parent feature. A feature could consist in a set of sub-features. And features could be mandatory, like this one for example. They could be optional, and sub-features could be exclusive, or a feature may consist on a concatenation of sub-features, or relationship. We could have also, as I said, dependencies between features. For example, we could say that, for example, this is just an example, an HD screen requires a double capacity battery, okay, or large capacity battery. So this is feature modeling. The very interesting thing about feature models is that they allow some kind of reasoning, which is very important then to generate products in the correct way. And so examples of reasoning algorithms are detection of dead features. So what a dead feature is that feature is a component or a feature that is never going to be included in any product of the software product line. For example, here we have double capacity feature. If we add, I have intentionally added this constraint that the CPU excludes double capacity, which is of course an incorrect constraint, but I just added to illustrate the proposal, the saying. So CPU is a mandatory feature that excludes double capacity, so double capacity is never going to be included in any product. So this is what we call a dead feature, and this is a bad thing in the software factory. Another reasoning algorithm is SPL validity. So we may ask ourselves, is our software product line valid or not? In this case, it's not valid because, for example, we have this exclusion constraint between two mandatory features. So the CPU is mandatory, the battery is mandatory, but are exclusive. So this is not correct, and software product line is incorrect. And another example of reasoning algorithm is we have a product consisting in configuration of or a set of features. So those who are green are included in the product, and those who are in red boxes are excluded from the product. So we have this configuration, and we would to ask ourselves, is this product valid or is not? So in this case it's not, because we have an HD camera. HD is supposed to require external, but external storage is not included in product, so we have an incorrect or an invalid product. Okay, so these are some examples of the reasonings we could do on the software factory. Of course, for small feature models or small factories, it doesn't make much sense, but in larger ones, it's very, very important. So here reasoning on variabilities and options. The existing approaches to reasoning on feature models usually use SAT and CSP solvers, and the main problem with this kind of approaches is that they consider direct dependencies only. Okay, let me explain myself. For example, we have a client. The client wants a phone with an HD camera, so we want to generate a product for this particular client. So what we do, or what the existing approaches usually do, is that they select the HD component here, it's in green. Then if you select the HD component, you know that when you select a feature, you need to select its parent feature. So we select camera. This is step one. We select camera feature. We deselect HD because it's exclusive with HD. We select HD because it's required. We select external because it's required also. Okay, so this is the first step. The second step is that since we have selected camera, we need to select its parent also. So we select smartphone. Okay, and third step, as soon as we have selected smartphone, we need to select all its mandatory features. So we need to select battery, CPU, screen, and audio input output. Okay? Fourth step, because we have selected battery, we need to select all the mandatory features of battery. So we select simple capacity. Fifth step, because we have selected the external storage, this feature, we need to select this parent feature also. So we select storage. Sixth step, we need to select HD screen. So yes, this is HD screen. We have to. Okay, sorry, I'm lost. Include required feature of HD screen. No, not. Yeah, the included. Yeah, the required feature of HD screen is double capacity. So we need to include double capacity also. And last, the seventh step is to exclude alternative of screen HD, because we have selected HD. We need to deselect SD because it is in exclusion with HD. So we have 7 steps just to generate to do one reasoning step actually, or configuration of our product. Okay, and the problem with this method is it is recursive. Okay, and for small feature models this is not much a problem, but for feature models with thousands and even tens of thousands of features, like the Linux kernel for example, this kind of operation may take minutes. Okay, so a whole operation can take even hours, and this is very problematic. So the idea is that what if we could know all the dependencies of a feature? If we can pre-compute all the dependencies of a feature, then setting a feature or configuring a product could be almost instantaneous. Okay, so this is the idea. So we, as I've said, we pre-compute all the dependencies of every feature. And for that, we use a Dijkstra-like algorithm. I won't go too deep in this because it's going to take time, but it's a very efficient algorithm, and it computes all the dependencies very quickly and then very quickly. So then we have, for every feature, it knows all the features that it directly and indirectly knows. So the direct and indirect requires of the feature, excludes of the feature, and we know for every feature what are the features that are required by this one. Okay? So we compute all these sets, and then when we set a feature, it sets automatically all the dependent ones in one step. Okay? So let's see the example again. So here, for example, we want to select the HD feature. So we pre-compute all the dependencies of HD. We have them here, here. Okay, there they are. I pre-computed them. So, for example, for HD, it's going to be the required HD are the camera because it is its parent feature, the smartphone because it is the parent of camera, the audio, screen, CPU, and battery because they are mandatory of the parent feature, etc. So we pre-compute them. Same thing for excludes. It excludes screen SD, and maybe I forgot the camera SD. Okay. So since we have this information, when I set SD, I automatically set all the others in one step instead of 7 steps. And this is what makes the reasoning on the feature model very quick. So this is the platform I have developed to use this idea of transitive feature dependencies. I'm working on the Moose platform on top of Pharo, so that I can reuse some of its analysis tools like visualizations and querying and things like that. I reuse the familiar project, which has been developed. So the familiar project, I've used mainly the FM meta model, and the familiar project, which has developed by, Alexandre Berger. And then I implemented here, so here I have this notion of transitive dependencies. I have implemented this algorithm, dependencies algorithm generator. And these are some of the algorithms, some of the reasoning algorithms I have developed on top of this transitive dependency idea. And visualizations, visual editor, external partition, and things like that. I'd like to develop them in the future. They are not done yet. Okay? So this. Now I want to evaluate my proposal, and I want to answer the question: are the algorithms that are based on transitive dependency faster than the ones from the literature? So to answer this question, I have compared two algorithms. Actually, they are genetic algorithms. The genetic algorithm from a reference genetic algorithm for optimal features selection, which has been proposed by Guillot et al. And I compared the result to my genetic algorithm based on transitive dependence. Okay, and I illustrate this on the problem of optimal features selection problem. So I have my feature model, and I want to find the optimal configuration of features that satisfies a certain requirement. Okay. So the experimental results are here. Here I have the number of features. So I started with 100 features and I ended with 2,000 features. Here I have the execution time for calculating the optimal configuration of features. And these are the results of Guillot et al. Genetic algorithm. And my results are just here. So I made 99% of gain of time. Okay, exporting this time. I encountered some issues though. So the first one is I wasn't able to create more than 5,000 features. 5,000 features because mainly because I had some memory problems with Pharo. So maybe using Spoor in the future will resolve this kind of problem. I had also this issue of actually the genetic algorithm of Guillot et al. Was faster or slower, sorry. It was slower compared to the results it's reported in its papers, and that was developed in other languages. Actually, it was developed in C, and the reason for this is that maybe he did some optimizations that I didn't myself, and this was intentional because I wanted to compare really the ideas, basically. Maybe the meta model also was a bit complex. The meta model I am using to perform my computations, and maybe this is more or less related to the Moose image and to the VM compared to the C language, which is normal. Okay. So as future works, maybe I would like to, surely I would like to implement the other tools, visualizations and the importer-exporter of the feature models and things like that. I would like to extend the meta model with things like attribute and complex cross-tree constraints, because we can have more complex cross-tree constraint than just require and exclude. And I would like to do more comparisons with other reasoning algorithms, and especially with this SAT and CSP algorithm, because I didn't compare to them yet deeply. Okay, so I probably need to do more comparisons. And yeah, I would like to talk about this genetic algorithms framework I have developed. The link is here. You can reuse it if you have some some optimization problem. This is meant to be very reusable, so there's the code. You can use or contribute yourself to this framework. And finally, I would like to thank the ESUC for supporting my work, and the INRIA laboratories, and especially Stéphane Ducasse, for inviting me and his team for 2 months and to perform this work. And thank you very much.
Again,